so projections, this is a type of projection, probably not one that you want to be really close to, right? So what we're talking about projections is we're talking about when something either gets thrown up in the air, when something falls off, meaning that it might have an initial velocity, but it has nothing else powering it at that point. As far as horizontal movement, we'll talk about rockets a little bit that might have their own propulsion for a period of time. So gravity is going to come into play, even with the volcanic, expulsion there. It throws it up, but then the only thing really acting on it is the initial velocity and then how far it's going to go horizontally and vertically based on the initial and the pull of gravity, right? And so that's really where we're going to go with these. The first question I asked, which we will finish up with this question when we end this section, is at what angle should a batter hit a baseball to get the most distance, right? Clearly every batter wants to know. And so that has to do with the propulsion, right? You're going to have an initial velocity for a baseball, but after that, there's nothing powering that baseball. And we talked a little bit about that when we talked about dropping things, gravitational pull for dropping things. And so you're going to see those formulas come back into play. Those formulas from chapter 2 that we talked about are going to come back into play with this chapter. And now we're going to throw in the velocity of it and how it's being affected. So a couple terms here that are new. Projectile is any object near the Earth's surface that is launched with an initial velocity and then moves under the influence of gravity. So a projectile, can have an initial velocity and then it is moving based on gravity. Based on gravity. That is your projectile. Projectile motion then is the motion of the projectile. That's pretty straightforward. Ideally with constant velocity, horizontal motion, and uniformly accelerated vertical motion. So constant velocity horizontally and uniformly accelerated, meaning gravity is uniformly accelerated. So the next term is trajectory, and that represents the path of the projectile. The path of the projectile is called the trajectory. Horizontal launch. So objects typically have both horizontal and vertical components. At this point, if you not recognize that we are breaking things into horizontal and vertical components, you may want to review your notes, right? These are independent but occur simultaneously. All right, so what that means is you have a horizontal component that might be affected by something, and then you have a vertical component that might be affected by something else. And while they're happening at the same time, they're not necessarily affecting each other. And so you can actually treat them completely as separate equations of motion. So that term equations of motion takes us all the way back to our original equations of motions that we had. All right, and so we are actually going to incorporate our first, second, and third equations of motion with vertical and horizontal movement. So we're going to have our horizontal and vertical movement with those equations of motions that we did a couple chapters ago. All right, so let's look at this. Here come the equations. All right, projectile motion is first we're going to talk about our horizontal component. Our horizontal component. If there is no horizontal acceleration, then you just have your v of x, which that should be a little sub x there, equals your initial velocity at x plus your acceleration times t. So then if you don't have any horizontal acceleration, so let's say there's nothing accelerating it horizontally, which the ones that we're going to do in this section don't, then you really just have your initial velocity being the same as your overall velocity because there's nothing else affecting velocity. What I mean by that is if something were to get shoved off a cliff, that initial shove is your horizontal velocity, right? But there's nothing else that is helping horizontal movement. Does that make sense? So however fast you initially shoved something off of a cliff is the initial horizontal, but there is no acceleration because there's no accelerant. There is no motor on it. There is no engine, right? There will be an acceleration vertically. It's called gravity. But horizontal acceleration doesn't happen here, all right? Because we don't have anything that's helping it move. If it were a car, once it went off the cliff, even that no longer has horizontal acceleration because my wheels aren't touching anything, right? Does that make sense? So what they're telling us here is that if you don't have horizontal acceleration, your initial velocity becomes your initial velocity of x horizontally, which just becomes velocity of x. Whatever it is, because it's not changing. Nothing is affecting that velocity. The second equation of a motion just becomes that velocity. So if you'll recall, we had our change in x is our final minus our initial. Well, now we're talking about velocity. Remember, we have final and initial that are not changing, so we just have our velocity of x times t. All right, so our change in position is just going to end up being, and remember, we're talking about change in position horizontally. Change in position horizontally then is going to be our vertical velocity, our horizontal velocity times our time. Okay, so we're just doing just horizontal components. Just horizontal components. My change in position horizontally is just going to be my horizontal velocity times my time. Horizontal velocity times my time. And in this case, we don't have a third equation of motion because we're only talking about horizontal movement, and our third equation dealt with gravity. Okay, so horizontal motion is all we're talking about. If we were to throw something off a cliff, we're talking about how far it moved left and right, horizontally. That's what we're talking about with these equations of motion. So you're looking at your velocity horizontally and your time. How long it moved in that direction horizontally. All right, let's look at vertical. Projectile motion, hopefully, and it's, oh, we repeated ourselves here. So projectile motion, hopefully you remember this first one, gravity. So gravity is 9.8 meters per second squared. If it will let me write it, that will be great. 9.81 meters per second squared. All right. The initial vertical velocity of a horizontal projection, which is what we're doing, is going to be 0. So vertical velocity then is going to be 0. You're not throwing something down when we do these. We're just doing horizontal projections here. Horizontal projections, meaning you're going to have an initial horizontal velocity, but you're not going to have an initial vertical velocity, okay? They're throwing it this way, horizontally, is what we're talking about, horizontal projections. So that means the initial velocity down is 0. We're not throwing something down. We're not projecting something down. We're doing it across right now, horizontal projections. So let's look at these equations. So then the first equation, my velocity then of my y, you'll notice those little subscripts are y final, is going to be gravity times how long it's falling, pretty much. Gravity times time. My second equation, so let's say I have that initial and final. Remember, initial is 0. My change in y, we have 1/2 gravity times squared. This is from our second equation of motion. So this is one of our second equation of motions from initially. And then our third equation, my y final, my y initial position here. And then I have my velocity, final velocity of y over 2 times gravity. So a couple things I want you to pay attention to. If you see the y here, I'm talking about y's position. Y's position. If you see the v with the little y, that's the velocity of y, okay? So when they're talking about something like this, they're talking about the position of y. You notice velocity is nowhere in this equation. So if I have just my position of y, I can calculate time because I know what gravity is. It's always the same. If I have a velocity at y, then I can use that to calculate time here. So it just depends on what you've been given in your problem. Have you been given a velocity? Have you been given a position? Have you been given an x velocity or an x position, okay? And so those are the things you're gonna look for, and you're gonna have to think about, what do I know? What do I need to get? All right, so let's look at the examples that they give us. First example here. First example, a drone is at an altitude of 11.5 meters and flying horizontally at a speed of 1.85 kilometers per hour. When it drops your physics study guide, that's what you want, a drone delivering your study guide. If air resistance is negligible, how far does the book travel horizontally before it strikes the ground? How long will it be in motion from the time it is dropped until it hits the ground? All right, so the first thing you want to do is you want to visualize what is happening. So if you have to draw a picture, it does not have to be that detailed, obviously. All right, you have something up here traveling horizontally. That is your drone. So up here we have this traveling horizontally, which means that if the study guide is inside of this drone while it is traveling, they have also given us an initial velocity of that study guide, right? Because it is currently in the drone going 1.85 kilometers per hour. So that's how fast it's going when it's dropped, which means that is my initial horizontal velocity. My initial horizontal velocity, we're going to label it V velocity X. Vx. How fast is this thing going horizontally? It is going to be in whatever it is being carried by. However fast that guy's going is how fast the study guide is going to be going. And so they gave that to us. 1.85 kilometers per hour is how fast that study guide is initially going. 1.85 kilometers per hour. They have also given me my change in y. So let's talk about this. We're going to assume, like we have, that initially the y is wherever it is. So we're just going to say my y initial. Remember, when I have the y there, I'm talking about position. Initially, that y is 11.5 meters in the air. When it lands, my final position of y, it's going to land on the ground, so it's going to be 0. Which means that my change in y is going to be negative 11.5 meters. It fell 11.5 meters. So we know all of that. So a couple things I'm going to point out, all right? Typically you want to change these to meters per second, right? Because if you do meters per hour, it's going to be really tiny, all right? So meters per second is what we're going to want to change it to. The reason I'm changing my velocity to meters per second is because the other unit of measure they gave me was meters, all right? So they gave me movement velocity in kilometers per hour, which is standard. But then they told me how high it was in meters. I have two different units. This is going to cause a problem if we don't do a conversion. So we're going to do that conversion that we've been doing. We are going to take this kilometers per hour. Remember, hour is in the denominator. So if you need to write it, you can write it in kilometers on the top per every 1 hour on the bottom if you need to do that for your conversion brain. Which means that I need to convert. So I need to do hours. I need to change that from 1 hour, 3,600 seconds. I need to change that 1 kilometer to 1,000 meters. And I need to do that conversion. So go ahead and do the conversion to meters per second for that velocity. Meters per second for that velocity. Go ahead and do the conversion and tell me what you get. You should have gotten 0.5139 meters per second, all right? Meters per second. That's how fast your study guide is traveling, all right? The next thing, all right, so it's asking how far it goes horizontally. Well, I know how fast it's going horizontally. I need to know how long it goes that fast, right? If I know how fast it's going and how long it goes that fast, I can calculate the distance. Rate times time. We've known that since Algebra 1, right? I need time. That's where my horizontal helps me, okay? So horizontal is going to help me because I know how long it fell. I know that the drone didn't throw it down. So the only force acting on falling is gravity. Does that make sense? All right, so we're going to go to our equation. All right, I'm going to put it up here at the top. My equation was, well, my final position should equal my initial position, all right, plus 1/2 gravity times squared. Well, if I move that over, so let's move my final over. Y of F minus Y of initial. Another way to write that is just my change in Y. Does that make sense? If I take my final and subtract my initial, I have my change in Y, which I actually already calculated. So that means, I'm running out of room for myself. That means that I can rewrite that equation at the top. Moving that I over, my equation looks like this. I have change in Y should equal 1/2 gravity times squared. And I know all of that stuff, don't I? What was my change in Y? My change in Y was that it fell 11.5 meters. We write that as a negative 11.5. That's my change in Y. Equals 1/2. What is gravity? We know that too. Negative 9.81 meters per second squared, right? Know that as well. The thing that we don't know is my time. Time squared is how that equation works. So solve. You're going to multiply by 2, divide by gravity, and take the square root. All right? So I'm going to multiply both sides by 2. So I end up having 2 times my change in Y. Divide by gravity. So 2 change in Y divided by gravity should equal my time squared. How long is this thing falling? How long does it take to fall 11.5 meters with just gravity being the force on it? How long does it take? So for homework, you should have set all of this up, hopefully just like that. You should have done your conversion. How many meters per second is that if you do that conversion? It is a beautiful 15, right? And if you wanted to write it with your significant digits, just to remind yourself of what they are, you can, or you can wait to the very end to worry about significant digits. All right, so we have this is my initial velocity just converted. I haven't actually done anything except a conversion here. All right, I am going to use my change in Y. Remember the formula that we used? We have my final velocity should equal my initial, or my final position should equal my initial condition plus 1/2 gravity times squared. Okay, I do not know my time. In fact, that's what I need to know to be able to figure out my horizontal position, okay? So final position minus initial is just the change in position, which we actually already know. Yes, my change in Y, I already know. That was negative 80. That should equal 1/2 gravity. I also know, negative 9.81. And time squared is what I'm solving for. All right, what is time? How long did it take for this if I did 3 significant digits for this? Go ahead and figure it out. Multiply by 2, divide by 9.81, and then take the square root. So change in time should have been 4.04 seconds. That's how long it took to fall. In the time that it was falling, it was also moving horizontally. Yes? Does that make sense? And so if I calculate my change in horizontal position, change in horizontal position is just my velocity horizontally times how long it moved horizontally. My velocity was 15 meters per second. My time was 4.04 seconds. I should be left with meters. How many meters did it move horizontally? How far horizontally will the package travel before reaching the ground? What was your answer here? 60.6 meters. That's how far away it will be from where they were on the, like if you were to go a straight line above that drone, when it dropped, it will be 60.6 meters away from that drop point. So they could have dropped it early, 60.6 meters early, and it would have dropped directly over, right? So frame of reference. The same motion when observed in different reference frames can appear different. We talked about that with the movement of the fly, right? So just because your point of reference changes doesn't mean the movement of the object itself is different, okay? It can look different, which is why, when someone observes a crime that happens, you get 4 different stories, because from their vantage point, they didn't see the guy had a gun because they were standing behind him, but the guy in front of him saw that he had a gun. Like, it's all about frame of reference. What actually happened is the truth, right? And so when you are doing these, you have to create a frame of reference. You have to create, okay, if this is my 0 and this is my horizontal, then I'm going below the horizontal. For example, if I'm at the top of the cliff, which is the example we're about to do, here I have a top of the cliff. If I have the top of the cliff, from my vantage point, that's going to fall below the horizontal, right? But if I'm at the bottom of the cliff, it is actually falling above me, right? And it's coming towards my horizontal. The movement of the rock itself doesn't change, though. The displacement of the rock itself doesn't change. How I describe it to you may, right? Based on my vantage point and my frame of reference. So it says a rock rolls horizontally off a cliff with an initial velocity, my guess is it was shoved, or it fell from above, of 10 meters per second. It strikes the ground 30 meters from the base of the cliff. How high is the cliff? What is the rock's total velocity just before it hits the ground? So we are coming to this from a different perspective. On the first one, we knew how high it was. We were trying to figure out how far it moved horizontally. For this one, we don't know how high it is, but we know how far it moved horizontally, right? So they've given us different variables that we now know, all right? So a couple things that we're going to do. We're going to write this stuff down. Initial velocity horizontally. So movement this way initially, they have told us that is 10 meters per second. So they actually tell us our change in x. Remember, when you see just the x, not the sub x, we're talking about position. They told us how far it moved horizontally. It started here, it moved 30 meters horizontally. It tells us it strikes the ground 30 meters from the base of the cliff. That is a horizontal movement that they just told us. That is 30 meters, all right? So just from those 2 things, I can actually figure out how long this was happening. Because we just used this equation a minute ago. If I have this is going to be based on how fast it was going for how long, right? If I know how far it moved and I know how fast it was going, I can figure out how long it moved. I just divide. So if I fill those in, I would say, well, it moved 30 meters. It was going 10 meters per second. It must have moved for 3 seconds. And I think I went ahead and kept my significant digits here. Yes?
So how would you solve that out if you were like still have it?
So you have it all written out. You're just going to do 1/2 times the 9.81 times the 3 squared, 9. Okay. Do your order of operations. Square this first and then do your multiplication. Okay. Mm-hmm. Questions on that type of problem? Questions? Good. All right, try one. Try it is the next one. I'm going to leave this up here because you have some different, this next problem is not set up identical. You're going to have to figure out, do I have my change in y? Do I have my change in x? Do I have my time? Do I have my initial velocity? What is it asking for? You're going to use all the same things. You're just might be given different variables there.